So with plug-in hybrid electric vehicles, we'll have the capability to charge the battery on board the vehicle. With that battery, we can do a lot of things more than just driving the vehicle itself. For example, if we look at the diagram here, we set vehicle to grid. Well, we have a vehicle that has a battery on board. Now that battery can be charged on your utility grid, whether it's AC or whether it's DC. Remember that in the near future, we're going to have more and more renewable energies available. All the renewable energies needs to be DC. Now they can be converted into AC and interface the current grid, but there's no need to do so because all the renewable energies themselves in the first stage is a DC source. For example, solar and even wind energy, we have to rectify them and somehow convert them back into AC. So with the plug-in hybrid electric vehicles available, with the battery on board available, we can charge the battery from the AC grid or we can charge the battery from the DC grid. On the other hand, we can also use the battery to help the power grid. For example, we can use this V2G concept, vehicle to grid concept. With this concept, what we are doing is we use the battery on board the vehicle to help the power grid to regulate the frequency, maintain the stability, because the energy on the battery can be pulled back to the grid. So if there is a huge demand peak coming from somewhere. Also, during the power outage, you can use the battery on board a PHEV to power your office and house. Now the battery, of course, may have limited energy available for a certain amount of time. But since it's a PHEV, you have an engine on board. You can basically turn on the engine and produce electricity through your vehicle and to power the office and the grid. So that's another advantage of a PHEV. This is a diagram that we discussed a little earlier, where you can see the power demand is higher during the daytime. At the lunchtime, normally it reaches the peak. But during the late part of the evening, it goes to the minimum demand. So the green line shows the power demand on the grid. If we have PHEVs all over in the place, we'll be able to charge the PHEV using the available power from the power grid, which is going to increase the demand at the late part of the evening. But until you have a really large number of PHEVs, that demand is not going to affect the grid operation. So we look at a number of architectures already, and we said there are 4 different types of PHEV and HEV configurations available. Among all those configurations, which ones are suitable for PHEV, which ones are not suitable? So we want to have a little discussion over here. PHEV maximizes the use of onboard electricity when the battery SOC is high. So that's where how you use the battery energy. So no matter whether it's blended type of PHEV or whether it's range extended HEV, you want to maximize the use of electrical energy on board. Once electrical energy on board is drained, and you can use the onboard gasoline or diesel to power your vehicle. In a range extended HEV, which is a series type of HEV, that is mostly suitable for a PHEV operation, apparently, because the electrical motor will be able to drive the vehicle, using the battery energy only. So there's no need for the engine to start as long as you have energy in the battery systems. But because this series or this range extended HEV needs a larger size electrical motor on board, so the cost of the system may not be competitive with a blended HEV. The normal operation would be you charge the battery to 100% SOC overnight, and the second day you will drive the vehicle, rely on the electrical energy until the battery SOC drops below 30%. Some designs may have a 40% threshold, some designs may have a 20% threshold. It depends on the control system design on the vehicle system. At that moment, you're going to switch on your gasoline engine. So your vehicle power is from your gasoline engine. So that's range extended HEV. That's again a series PHEV. In the blended PHEV, which is a type of parallel HEV, well, the motor size is not large enough to drive the vehicle alone at high vehicle speeds and high acceleration needs. So therefore, the motor will only satisfy the driving at low vehicle speeds. Some vehicles will be able to be driven for up to 40, 45 miles per hour or 50 miles per hour with gentle accelerations, and some vehicles may be able to be driven for up to 39 miles per hour with gentle accelerations. So in that case, when your vehicle approaches high speed or when you need certain accelerations, your engine will normally start. But once you get to a cruising speed which is below the threshold speed, your vehicle engine will be turned off. So you're going to maximize the SOC use, maximize the energy use from the battery. Once the battery SOC drop to a certain limit, for example 30%, you're going to turn this vehicle into a regular HEV operation where it's still going to take advantage of the HEV. Because you have a larger battery, you actually have more opportunity to recover regenerative braking, so which means you're going to recover more braking energy. In this case, your fuel economy will be still better than a conventional HEV. So this is how you operate a blended PHEV. A blended PHEV is a parallel HEV, or it can also be a series parallel HEV, or can be a complex HEV. But in general, it's a parallel operation. The other types of hybrid electric vehicle, if the electrical motor size is small enough, you are not able to use it as a PHEV because the motor may not be able to drive the vehicle anyway. For example, some of the HEVs in the market has a motor rated at 15 or 5 or 10 kilowatts with ISG, integrated starter alternator type configuration. Those vehicles are not suitable to be built as a PHEV. So typically, if you look at this chart, that if it's a blended PHEV, the motor size needs to be roughly 50 kilowatts or more for a passenger car, for sedan, compact or a full-size passenger car. If it's SUV, you're going to need a little bit more power. So usually you will need a motor at 75 kilowatts. If it's a series or range extended HEV or full PHEV, you're going to need a motor size at least 125 kilowatts for a passenger car and probably 150 kilowatts for SUV. Of course, the exact size of the motor, exact rating of the motor needs to be designed according to the type of vehicle, the weight of the vehicle, the acceleration needs, the top speed, and so on. So this is, again, just roughly give you a rough idea of what type of motor needs to be placed in a PHEV, in a range extended EV, and in a blended PHEV. In the vehicle, all kinds of vehicles, we need to evaluate their performance in terms of their fuel economy, driving distance, the emissions, and the acceleration performance. In a PHEV, we need to do similar things, but it's more complicated because a PHEV would have different evaluation criteria than a conventional vehicle and a conventional HEV or conventional just gasoline-powered vehicle or a HEV, because there's energy charged from the power grid. So how do you evaluate that type of performance? Okay. Now let's look at a few things here. The RE-EV is suitable for any driving cycle. That's not a concern. You can drive at high speed, highway, local accelerations without starting the engine. So that's easy to evaluate RE-EV for their driving distance or for their electrical driving distance. A blended EV is, on the other hand, is more suitable for city driving, for daily commuting purpose, stop and go situations, because the motor size will not allow you to drive at high speed without starting the engine. But in both vehicle systems, the purpose is to displace the fuel usage during the first set of driving cycles, which means the purpose is to drive the vehicle for a certain distance without starting the engine or minimum operation time for the engine. So the benefits will be further enhanced by designing the driving cycle based on designing the driving or the vehicle control based on the person who drives the vehicle, or based on the driving pattern or the distance or the kind of route that you take for that vehicle. Application of PHEV, well, you can use this PHEV for many applications. Apparently, the ones that are most suitable for PHEV included are passenger cars that are mostly used for daily commuting purpose, and pickup trucks, SUVs, that are again used for daily commuting. Those vehicles, the SUV and the pickup trucks, they have very low fuel economy. So making a PHEV on those vehicles will have a more significant impact on the fuel savings. We'll look at that in the next few moments. Delivery trucks are most suitable for PHEVs because delivery trucks, the driving distance is not very long. They usually have a fixed driving pattern for the vehicle. And so that's a great opportunity to charge the vehicles and then drive them on daily delivery routes. In airports, factories, parks, rural and many areas, so that you use the vehicle to carry passengers around. So there are opportunities to use PHEV. Well, you really don't, or even a PHEV, because the driving distance again is not very much, and the driving at a low speed and stop and go situations. Utility vehicles, yard tractors. Now, one example is a utility vehicle. A utility vehicle, you drive the vehicle to somewhere, you stop there, you are doing some work. For example, repair the power lines. So at that moment, if you use a traditional vehicle, you need to keep the engine on, to have other functions, for example, the hydraulic lifts and so on. If you have a PHEV, there's no need to keep the engine on because you will have your battery to provide power for the auxiliary needs. Once the battery power down to very low, you can start the engine to charge the battery for a few minutes, say 5 to 10 minutes, and then you will have sufficient power to operate for the next hour or two. So therefore, you are greatly reducing the energy consumption on a utility vehicle. So those are the areas that we have opportunity to use PHEV, that we not compromise the driving performance, but we're providing great opportunities for fuel consumption and emission reductions. The next topic is to talk about electrical driving range of a PHEV. Now, again, as I mentioned, for a range extended EV, it is very simple to calculate the electrical driving range, because you start the vehicle with battery full, and you measure the SOC. When the SOC reaches 30%, that's where you have to start the engine. Right before you start the engine, then you measure how long you have been driving the vehicle, and that distance is your electrical driving range. That's very easy to measure. The only thing that you may have to worry is that how you can customize the control of the vehicle so that it will better suit the driving needs, the vehicle demand, so that you can consume less electrical energy but giving more distance for the same energy stored on the battery. But for a blended PHEV, that's very tricky. For a blended HEV, if we can maintain the speed of the vehicle at very low, you will not need to start the engine. In that case, you can easily measure how much distance you have been driving the vehicle. But in most of the cases, it's very hard to maintain the vehicle at a low speed. For example, on the daily commuting. So you have to reach a certain speed at a certain city roads or even on local freeway. So in that case, the engine will start. When the engine starts, you're going to consume some fuel. Therefore, even though you're using most of the electrical energy, but you're consuming a little bit of fuel within that distance you're driving. So how do you know how much is electric and how much is by fuel? So that's something we need to know. And by the way, you can also customize the vehicle control so that you can take more advantage of the battery energy instead of the engine energy or the fuel. So therefore, there are different ways to look at electrical driving range. But the basic idea is that you want to compare a blended PHEV with a HEV in the same type. For example, if somebody drives a Prius hybrid and another person is driving a Prius plug-in hybrid. Now both vehicles are very similar, except that the weight may be a little different on the plug-in because you have more batteries on the vehicle system. But other vehicles, otherwise, the two vehicles are very similar. So when you drive the two vehicles for a certain distance, and one consumes a certain amount of fuel, the other one consumes a certain amount of fuel. So you compare the fuel consumption, you can get a conclusion on MPG. Okay. Now this example, we look at the example here. You look at the chart. Suppose that person drives the regular HEV that has 33 miles per gallon. 33 miles per gallon. So for 1 gallon of gasoline, he would be able to drive 33 miles. That's what it means for 33 miles per gallon on that HEV. Now another person is driving a blended PHEV that has 50 miles per gallon on the first 50 miles of range. Okay? But after 55 miles, the vehicle will run back to 33 miles MPG, or maybe a little better, maybe 35. But it will basically run back to a normal MPG. So if I give 1 gallon for gasoline to the two people, the first person will be able to run 33 miles, but the second person will be able to achieve 50 miles on the same gallon. So the difference is 22 miles. The difference is 22 miles. Where is that difference coming from? The difference is coming from electricity, electrical energy stored on the battery. So this 22 miles is the equivalent electrical range of that PHEV. So apparently you can see that 22 miles is not realized within the first 22 miles of range. It is realized within 55 miles of range. So which means if your driving range is less than 55 miles, you're not going to get 22 miles electrical range. You're going to get, what it means that you're not going to consume all the energy in the battery. Okay. So that's the trick, that when you design a blended PHEV, so how much distance can you drive before you consume 100%, not 100%, maybe 80% of the energy on board the battery? So that's important. If somebody, let's say, he drives only 20 miles per day on the daily commuting, and he buys this PHEV that has 50 miles per gallon on the first 55 miles range, it does not make sense for him because every day he would only drive 20 miles. He's not taking advantage of all the electrical energy on board the PHEV. A second example is that, okay, let's reduce the range that has a high MPG. So in this example, the first person is driving a regular HEV that runs 33 miles per gallon. But the second person is driving a PHEV that can give you 65 miles per gallon on the first 43 miles. So after 43 miles, the vehicle will go back to a regular HEV. So it's roughly 35 miles per gallon. So for the first 43 miles, the second person would consume 0.66 gallons of gas. Because that 43 miles, that is where he can achieve 66 miles per gallon. So for that range, he will need 0.66 gallons of gasoline. For that amount of gasoline, the PHEV would be driven for 43 miles. But if I give the same amount of gasoline to the first person, how long would he drive? How much distance can he? Because he is driving 33 miles per gallon, so for 0.66 gallons of gas, he can drive 33 times 0.66, he gets 22 miles. So for the same amount of gasoline, the first person gets 22 miles, but the second person gets 43 miles. So the equivalent electrical range is the difference between that two, which is 21 miles. So I'm using these two examples to illustrate that even though the two PHEVs, one claimed to be 65 miles per gallon, the other one claimed to be 55, but they have a very similar equivalent electrical range. One is 22, one is 21 miles. Okay. So it depends on what you are looking at and how you design the vehicle system. And you can achieve certain equivalent electrical driving range. You may have heard on the newspaper and on the news, on some conferences, and people have designed a PHEV that can achieve 100 miles per gallon, or they can achieve more than 120 miles per gallon. You got to ask them how much range you can achieve on that 120 miles. If they only achieve 10 miles range, that's probably not going to help you very much, because after 10 miles it run back to a regular HEV, so electrical range is very limited. But if they can run up to 65 miles on that 120 miles per gallon, it makes more sense, because it gives you more equivalent electrical driving range. So since I mentioned about 120 miles per gallon, we want to look at another example that claim to be able to achieve 120 miles per gallon for that PHEV. So now I give a little bit different perspective. So that HEV, the first person drives, can achieve 40 miles per gallon. The second vehicle is a PHEV. It's a blended type PHEV that can be driven for 25 miles at 125 miles per gallon. So what it means that after 25 miles, the vehicle will go back to roughly 40 miles per gallon. So only for the first 25 miles, he can achieve 120 miles per gallon. So let's calculate. If the second person with a PHEV that he drives 25 miles, because that's a high MPG that he can achieve, how much gasoline would he consume? Well, because it's 120 miles per gallon, we simply use 120 miles per gallon to calculate the gasoline that he needs, which is 0.208 gallons of gasoline. So again, let me repeat. So this person is going to consume 0.208 gallons of gasoline for 25 miles. And after 25 miles, he would be just regular HEV. So for the same amount of gasoline, if I give the same amount of gasoline to the first driver, how much distance can he drive? Well, because he's 40 miles per gallon, so for 0.208 gallons of gas, he can achieve 40 times 0.208. He would get 8.3 miles. So that's what the first person would get. The difference between these two is the equivalent electrical range. So if we take these two, you can see that the electrical range is 16.7 miles, 16.7 miles, which is actually less than the first two examples that I gave you. So this example would illustrate that the MPG for PHEV may not make too much sense unless you specify the range for that MPG. If somebody tells you that he can have 120 miles per gallon vehicle that can be driven for 400 miles, that would be phenomenal. I mean, your electrical range will be so large that it will give you a lot of reduction in fuel consumption. But that's not going to happen because most of PHEVs will have limited amount of energy available from the onboard battery because of space limitations, because the cost that is associated with the batteries and so on. Okay. So to design REEV, you're going to be much better because if your PHEV, in this case it's a true PHEV, your daily commuting is 40 miles, mostly city. So if it's a REEV, we will basically just design the EV that is the REEV that can be driven for 40 miles on electric. So you're done with it. Okay, if you design the battery with that size that provides enough energy for 40 miles electrical driving range, your vehicle is good. But if it's a PHEV, if you design your equivalent electrical range to be 40 miles, the design is definitely wrong because that person is only driving 40 miles, that he cannot realize that 40 miles electric driving range on a blinded PHEV. Because he's driving only 40 miles, a good idea is that to realize a high MPG within first 40 miles range. So what it means that you design blinded PHEV. For the first 40 miles, you're going to get really high MPG. So he can take advantage of the onboard electrical energy. After 40 miles, you don't care because after 40 miles, you can be just HEV, which still give him a better fuel economy than HEV, but it doesn't matter because it's not driving more than 40 miles. For example, if you tell him that you can achieve 100 mpg for the first 40 miles, that will really give him a lot of advantage. So consequently, if you design a vehicle that has 60 mpg, but you only realize that you will realize at mpg within 80 miles, you see, he's not taking advantage because he's only take 50% of the electrical driving range, because for the rest of the 40 miles, even though you still have high MPG, which again uses electricity to increase MPG, but he's not taking advantage of that part. Now, if you give him another vehicle, which is a PHEV that has 120 MPG, but that MPG is only available for the first 20 miles, which is also not going to help him because he's going to have advantage, yes, for the first 20 miles, but for the next 20 miles, he run back into a regular HEV. So he's not taking advantage for the next 20 miles. So he's only using the first 20 miles. He has electrical driving, but the next 20 miles, he's run back into a regular PHEV, a regular HEV. So in this fourth scenario, the REEV with 40-mile range makes a lot of sense. The second scenario makes also a lot of sense for blinded HEV, 40 miles with high MPG. But the third and the fourth scenario, which either has 80 miles high MPG range or has 20 miles high MPG range, they both do not work very well for this driver. So that has to be considered when you design your plug-in hybrid electrical vehicle systems. Now, of course, each person's driving is different. One design cannot fit all, that's for sure. But it is always possible for blended PHEV design to customize the vehicle control or put some type of learning algorithm in the vehicle system so that the vehicle adapt to the driver's drive pattern. So gradually to learn how to operate the vehicle in its best way so that you give the most advantage to the vehicle's owner. I also want to mention that there are some design considerations when you consider what to do and what type of vehicles we need to consider to develop them as a PHEV. In America or anywhere else in the world, there are a number of different types of vehicles, including small compact cars, SUVs, pickup trucks, and large cars. Now, people have some preference to choose what type of car they buy. Now, ideally, we would want most people to go with a smaller car because that will give you much better fuel economy. And we would encourage people to take public transit, to take public transportation. That would be the best solution. But apparently, that cannot satisfy the diversified needs of different people. So large cars, including SUVs and pickup trucks, are going to exist in any society. Even though we want to encourage them to buy smaller cars, but that's not going to happen. So when we look at the different categories of cars, different cars will have different fuel economy. Large cars will have less fuel economy. They consume more fuel within the same driving distance. When we convert or when we build hybrid electric vehicle or plug-in hybrid electric vehicle to replace these cars in their respective categories, they will have a very different impact. Now we'll look at the chart on this example. The displacement of fuel in low MPG cars can save more fuel, which means large cars. What it means, large cars will displace more fuel if you convert them into a PHEV. Look at the example here. If you get a car that has a 13 mpg, every year if you drive 15,000 miles at 13 mpg, oh, this is a typo. With the 13 mpg, you're going to need 1,154 gallons of gasoline. If I increase the fuel economy by 38% on that car, converting into HEV or PHEV, you're going to 18 miles per gallon. So with 18 miles per gallon, if you again driving 15,000 miles per year, you're going to consume 833 gallons of gasoline. The savings on this is 320 gallons of gas on this car. So it makes a lot of difference. However, if you have a car that is already 50 mpg, like the Toyota Prius, it's already have a close to 50 mpg. If you drive the same distance per year, you're going to consume only 300 gallons of gas. And if you're going to 100 mpg, which you double the mpg on the car, for the same distance, you're going to need 150 gallons of gasoline per year. So the savings on this one, is 150 gallons of gas. There's no way you can save more than 300 gallons of gasoline because your annual consumption is only 300 gallons on that 50 mpg. So there's no way you can save the same amount of gasoline as the converting a large car into a high fuel economy car. So that's the idea. So similarly, we can do this in the Asian type of calculation, where they calculate the fuel consumption per 100 kilometers driven. So in this example, the distance is 25 kilometers per year at 17 liters per 100 kilometers distance. So the fuel consumption is 4,250 liters. If you increase again 38% fuel consumption reduction, you can get 3,000 liters per year. So the savings is 12,050 liters per year. Similarly, on a smaller car, if you only consume 4.4 liters per 100 kilometers, 1 year you only consume 1,100 liters of gasoline. So there's no way you can save 1,200 liters of gasoline per year. The maximum savings, you can double your fuel economy. You can save 550 liters of gasoline. So that's on the PHEV electrical range, fuel economy, and fuel savings. So in a short summary, the MPG in a PHEV may not make a lot of sense. It's the equivalent electrical driving range that makes sense to the driver. On the other hand, a REEV or extended range electrical vehicle or a full PHEV can have a certain pure electrical driving range, but a blended PHEV will only take advantage in a certain driving distance. So the MPG and the associated driving distance that give you high MPG is the one that makes sense. The equivalent electrical driving range has to match the driver's needs. So if the driver's daily commuting distance is 40 miles, you best deliver a PHEV that has high MPG within 40 miles. A vehicle that has high MPG for the first 80 miles does not make sense in this scenario. Similarly, a PHEV has very high MPG for the first 20 miles does not make sense in this scenario. However, if the person's commuting distance is 20, daily commuting is 20 miles, that very high MPG with 20 miles high MPG range will make a lot of sense for that driver. Okay. To design a PHEV, so you will first need to know what type of PHEV you're going to design. At the moment, blended PHEV would make a lot of sense because a lot of the HEV is designed as a parallel or series parallel or even a complex HEV where the electrical motor is in parallel with the engine. In that case, the electrical motor is a lot smaller than a series hybrid. The second wheel, the GM new PHEV, or they call it REEV, is a range extended EV. So in that case, it is a series hybrid, so the design is a lot simpler. But again, that's a unique design that has to be designed from scratch, because if you want to take a current HEV available and convert them into a PHEV by adding a large battery pack, whether it's done by an after converting company or whether it's done by an OEM, you have to think about a blended HEV. So the next topic, we're going to look at the powertrain coupling mechanism in a blended PHEV. In this topic, we're going to look at the differences between torque coupling, look at the slide, speed coupling, torque coupling. So those are the two major coupling mechanisms for parallel HEV and series parallel HEV. And the third one is the planetary gear-based eCVT or electrical CVT. CVT stands for continuous variable transmission. We look at planetary gear-based electric CVT HEV powertrain. After that, we're going to look at the GM two-mode HEV design, a dual-clutch transmission-based HEV powertrain. Also, our HEV powertrain developed by Professor Chai of UC Davis, the Timken's two-mode hybrid, and Renault's two-mode HEV. So we look at how the powertrain is mechanically coupled in all these different HEV configurations. So this portion is going to take roughly an hour and a half. So we're going to first look at torque coupling of a PHEV. In the torque coupling, apparently if you look at the diagram over here, it shows two input shaft and one output shaft. The two input shaft in this case would refer to a gasoline engine or diesel engine and an electrical motor. So there are two shafts coming into the mechanical coupling. There's one shaft coming out which would go to the final drive. And the box stands for mechanical coupling, which we're going to look at how they couple these two inputs mechanically. Since we're looking at, we're calling this torque coupling, by its name, we're adding the torque of the two input device. Now we're not exactly add them one by one, so we may be adding them with a gear ratio. So that's why the output torque is T1 times the ratio times T2 times the ratio. So there's the equation here to express T out is K1 times T1 plus T2 times T2. Since we're adding the torque, so the speed are not changed. Or in other words, the speed of the output is proportional to the two input speeds. So all the three speeds are proportional. How do you do mechanical coupling? In fact, there are a number of different ways to do mechanical coupling. On this diagram, we have three different methods to do the coupling. The top left diagram shows gear coupling. The top right corner shows a belt or pulley type of coupling. And the last one is to show a common shaft coupling. So let's look at them one by one. The gear coupling, we can have two different coupling mechanisms. The first one is using 3 gears. So the two input shafts on the two separate gear, the output is on another gear. So when the input T1 and the T2 is driving, so the T3, the output is coupled. You can have T1 freewheel, so T2 will be driving the vehicle. You can have T2 freewheel, so T1 will be driving the vehicle. Or you can have both T1 and T2 providing torque, so the output will be the summation of T1 and T2. If your output is less than T1, let's say T1 is providing torque, but the output is less than T1. So the difference between T1 and T out can go to T2. So T2 now become a generator. So it takes power from the mechanical coupling. So that's one gear coupling. If you look a little towards the right, there's another gear coupling mechanism. In this case, we eliminated one gear. So the output, the T out, is directly connected to T1. So in this case, the speed of input shaft 1 is the same as the speed of the output shaft. And T2 is added onto a gear which is connected to both T1 and T out. So in this case, if T2 is freewheel, then the torque of T1 will be directly transmitted to T out. If T1 is a freewheel, and then T2 torque is transmitted through gear to T out. Okay. Similarly, if T1 provides torque more than T out, the difference between T1 and T out will go to T2. So T2 is negative, which means T2 is having a torque driving the motor connected to T2. So that's the gear coupling. Now we move to the next block is about a pulley type coupling. In fact, this pulley coupling is exactly the same as the gear coupling. The difference is that we replace gear with a pulley. Okay. So you can have 3 shafts or you can have 2 shafts. With 3 shafts, the 2 input shafts are linked to engine and motor separately, and the output shaft is connected to the final drive. In the 2-shaft design, the input shaft 1 is connected to engine, the input shaft 2 is connected to motor, and output shaft is connected to the final drive. And the 2 shafts are linked by a pulley. So that's the second design. Move down to the bottom, we have a common shaft design. In this design, the motor is put on the same shaft as the engine output. Or the motor can be actually put either before or after the transmission. Then we will look at the two different coupling later. But the motor is on the same shaft as the engine, therefore the gear ratio, there's no gear ratio. So the engine speed and the motor speed are the same. So the motor can add torque to the output shaft of the engine, or the motor can also take the output of the engine to become a generator. So in case the vehicle demand is less than the engine can provide. So that's the third coupling mechanism. If we look at the three different coupling mechanisms, there are a number of vehicles that have been using different coupling mechanisms in the marketplace. For example, the Honda Civic is using the third coupling mechanism, while they're using the common shaft. Okay. If you happen to know the center wheel green line, which is on the marketplace right now, not the two mode, but the center wheel ISG type hybrid. So that one is using the pulley type of coupling mechanism. And if you look at the Eaton's delivery truck design, so that one is using the gear-based coupling mechanism. So they are all used in different vehicles. And later on, we'll have an opportunity to look at a few different type of vehicles that use different coupling mechanisms. Now, as I mentioned that the coupling can be before or after the transmission. So in this diagram, you are seeing an architecture that use two transmissions. The coupling is after the transmission. So the engine is connected to a traditional transmission. That output is connected to a mechanical coupling. The mechanical coupling is linked to the final drive. The electrical motor is also through a gear system and then connected to the mechanical coupling mechanism. So the electrical motor connect to transmission 2. Now this transmission 2 is not necessarily meant to be a CVT type transmission. It's simply a gear reduction. Now the reason you need a transmission to for the motor, because usually in a hybrid we design the motor with a high rated speed, which means the motor speed is much higher than the wheel speed. So in that case, we're going to need to gear down the motor speed. The reason we need a high-speed motor because we want to reduce the size of the motor. So you have the motor at high speed, then you have the vehicle at a lower speed. So you need gear between them. So this gear is for the purpose of reducing